The objective of this video is to determine the design section moment capacity of the grade 300 800 welded beam 122. Now for the case of 800 welded beam 800 WB 122 grade 300, we take Fy value 300 megapascals. Now that Fy value is taken from one steel tables. So if you check on the page number 11, on page number 11 we have a 800 WB 122. we have a flange value 300, wave value 310. We take the minimum value, which is 300 megapascals. So that is 300 megapascal. Zx value on page number 10, on page number 10, 800 WB 122, we can find the Zx value, which is 3970 at 122 times 10 to the power 3. So that is Zx value, section modulus. And then Sx value 4550. Sx value next to this one is 4500 times 10 to the power 3. So that information is extracted from the one steel tables. Also I draw these figures for these 800 WB 122, 250 millimeters. So if you are checking here, 250 millimeters is the width of the flange, that is 250. Thickness of the flange 16 millimeters, that is given here, 16 thickness of the flange 16 millimeters. Then we have a 792 is a depth, so 792 is the depth, D 792. And we have the 760, which is the depth between the flange. And I think the wave thickness is given 10 millimeters. So in here wave thickness is 10 millimeters, that is given. So you can extract this information from one steel tables, which is 10 millimeters, extract from one steel table, so which is 10 millimeters here, thickness of the wave. Now first of all we are working on the flange. The flange is this one. Now for the flange we need the B value, which is this outstand, which can be found 250, take away this 10 divided by 2, so B value is 250, take away thickness divided by, so 2 is 120 millimeters that we found. Thickness is 16 millimeters, thickness of the flange is the 16 millimeters. So this is the flange that we talking about. So now plate slenderness, the equation is lambda E B on T Fy on 250 square root. Now that equation is taken from clause 5.2.2 on page number 50. On clause 5.2 section slenderness, it has given this lambda E equations. We substitute the values. 120 we calculated, divide by 16. 300 we noted this one, divide by 250, give us 8.2. Once we find this lambda E value, we can extract two values, lambda EP, which is plastic limit, and yield limits for the flange, and that is given in table 5.2 on page number 51. So I can show it that table here. For page number table number 5.2, you have plate element type, which is flat, and longitudinal edge is supported 1 and is uniform compression. So you can imagine that one longitudinal edge, if you have this one, this is the flange, and we are saying that this longitudinal edge is one edge is supported, so therefore we have 1, and that is under uniform compressions, and this is heavily welded longitudinally. So we have this welded beam, so we are taking HW. So plastic limit is 8 and yield limit is 14. So that was written here, plastic limit is 8, yield limit is 14. Then we take the ratio lambda E over lambda EY, which is 8.2. We calculated 8.2 in the previous step. We calculated lambda E previous step 8.2, that I substitute here, divided by 14, that we just got it here, is equal to 0.54. Now for a wave, we have this B value, which is between this and this, and the thickness of the wave is 10. So 760, which we get it in from this figure, 760, and the thickness is 10 millimeters. Now plate slenderness, again the same equations that we use it in the clause number 5.2.2 on page number 15. We can use the same equation for wave. Substitute the values 760, 10, Fy 300, 250, and that is given 83.2. Then you have again lambda EP and lambda EY value from table number 5.2 on page number 51. Now our both age are supported, and for any section we have 82 and 115. So we have 82 and 115 plastic limit and yield limit, and we take the ratio lambda E, which is 83.2, and lambda EY 115, that is given is equal to 0.72. Now we compare these two values, 0.58 and 0.72. The 0.72 is larger value for the wave, so we can say wave is a critical. So we are designing on the wave. Wave is going to fail first, not the flange. So wave is a critical one. Now for that case we working on the wave. Now as you know, wave is a critical, so we going to have a lambda S is equal to lambda E 83.2 that we calculated for the wave, 83.2. Lambda SP value is equal to lambda EP, which is 82. Lambda SY is lambda EY, which is 115. Now once we have a close 5.2.4, just below the table 5.2, we have lambda SP less than lambda S less than or equal to lambda SY. In that case is a non-compact section, so we can compare. Lambda SP value is 82, so we have this one 82, we have this 83.2, and lambda SY is 115. So this condition that is given in this close 5.2.4 is satisfied. In that case we can say section is non-compact. Once you have a section non-compact, in that case we have a value of section effective section modulus ZE is equal to Z, and that big two brackets. So Z plus Z lambda SY minus lambda S over lambda SY minus lambda SP bracket ZC minus Z, that is taken from close 5.2. Now this ZC value can be taken of minimum of 1.2, so that is here. ZC value is taken from minimum of, that is written here, plastic and elastic modulus, which is the lesser of S and 1.5 Z. So that is how we calculate the ZC value. So we substitute Z value 3970 times 10 to the power 3. At the start we recorded that ZXL value from the one still tables, that is 3970 times 10 to the power 3. Lambda SY, we just calculated lambda SY taken from table 5.2, that is 115. Lambda S we calculated 83.2, lambda SY 115, then 82 is lambda SP, and then we have ZC value, which is ZC is equal to SX for the compact sections, and for SX we get this 4500 times 10 to the power 3, that is ZC minus Z 3970 times 10 to the power 3, that is your Z value here. Simplifications give 4530 times 10 to the power 3. Now these values also given in the one still tables, so if you make a mistake then you can confirm it here on page number 11. 800 WB 122 and ZEX value is 4530 times 10 to the power 3. So that's, you can check it with the one still table. So these answers is already given in the one still table, so we can compare it. Once you find the effective modulus, the last step is to find the design section moment capacity MS, and MS has a equation ZE times FY, and that equation is given in close 5.2.1. MS is equal to Fy times ZE on page number 50. In that case we substitute ZE value, we just calculated ZE value 4530 times 10 to the power 3 times 300 Fy. We get, this is Newton into millimeters, so we need to divide it by whatever the whole, we need to divide by 1000 times 1000 to convert into kilonewton meters. We can multiply by the steel safety factors, 0.9 times 1359, we get 1223 kilonewton meters. That is answer. Section capacity is 1223 kilonewton meters. Thank you.